If polymer membranes based electrolytes have been used from the later 2017 only. So the M1 later on to the M1 based materials, the vanadium based materials also show an extraordinary electrochemical performance for batteries. The major objective of my research is, first we will be dealing about the earth abundant high efficient cathode materials we will be preparing using hydrothermal technique, and then we will be study the electrochemical performance of the cathode material by tuning the morphology followed by appropriate surface modification by nanocomposite and nanohybrid architecture, and to further investigate the structural and chemical stability, and in order to reduce the irreversible capacity loss of various vanadium-based nanohybrid cathode and ohmic polarization loss by enwrapping and decoating the surface functionalized conductive additives, to develop a firm understanding of structure properties, performance relationship, and the high energy discharge capacity of this vanadium-based nanohybrid cathode. Electrode materials can be categorized into three categories: layered type and tunnel type, Nasicon type. Particularly for zinc-ion battery, the layered type material show an extraordinary capacity and the increased cycle number and increased capacitance retenuation when compared to the all other tunnel type and Nasicon. Here we will come to the fabrication of electrode material. The negative case, the first with the positive case, working electrode separator, and then zinc sheet, spacer, spring, and then negative case. Here we can use that anode as a zinc sheet and zinc sulfate as an electrolyte, and the working electrolyte plus carbon black plus PVD plus NMP in the ratio of 7:2 is to 1 we will be using for the battery fabrication technique. And further we will be dealing with the physical characterization like XRD, Raman, XPS and TGA analysis. Further to morphological characterization like FSM analysis and TEM, and later on to the electrochemical workstation. Let me discuss here with the two experimental works of my previously published data. First work describes about the morphology retained growth of V2O5 by oxidation of V-mexine as a fast diffusion control cathode material for zinc ion battery. Here what I have done is, first I have prepared an vanadium based carbide material mexine, and I have used an hydrothermal heat treatment with various heat temperature at around 160, 180 and 200 degrees centigrade. I noticed that the 160 degrees centigrade, the formation of V2 is very low and incomplete oxidation. Whereas in vanadium at 180 degrees centigrade, it shows a consistent growth of crystalline V2O5 nanorod on the external surface and with the existence of stacked layers. In V200 degrees centigrade, a well aggregated thick rods of V2O5 disappear from the stacked layer of V2C, and the existence of various morphology demonstrates that mexine can be used as a facile precursor for creating a tailored and unique morphology. Here in this XRD also you can able to clearly see that at 180 degrees centigrade mexine, we could able to see that the V2C peaks have been combined with the V2O5 peaks also. To the Raman spectra and XPS analysis, in Raman spectra we can see that at around 180 degrees centigrade the mixed state of vanadium at 180 as V2O5 and V2C have been present, whereas in V200 degrees centigrade only we could able to see the V2O5 peaks have been predominantly present, and in X-phase analysis we get to know that it is of a multi-oxidation state was present with the state of V4 plus and V3 plus, V5 state have been present, and in C1s also denotes that the oxygen content and carbon content are been double bonded to each other. When coming to the CV characterization of curve, in that CV curve at a fixed current rate of 1 millivoltage, I could able to see that at 180 around 180 degrees centigrade sample shows then better capacitance when compared to the 160 and 200. So further we move to the further we have done the we have varied the current with the 0.5, 1 and 2 for fixing 180 degree centigrade sample at different sweep rates 160, 180 and 200 degrees centigrade. With it, I can able to clearly see that at 180 degrees centigrade, the rate performance was more stable when compared to the 200 degrees centigrade. Whereas in 160 degrees centigrade, it is also stable, but the decreased capacitance can be lead because of to the only magazine content present in it, and it also showed an 89 percentage of capacitance retenuation when compared to the V2C at 160 and 200 degrees centigrade. The Nikos plots at V 180 degrees centigrade shows the much lesser resistance when compared to the all others. So the key findings of this research is that the V2O5 nanorod firmly embedded internally on the surface of V2C and provides an enough electroactive surface on Zn2 plus ion for integration and deintegration between the electrode interfaces. The synergism enhanced kinetics and additional zinc storage sites provided by the partially grown V2O5 nanorods and carbon defects at the edges and ensuring the high rate capacity of V2O5 at V2C cathode. The introducing of oxygen vacancy can compensate the internal non-zero dipole moment of the V2O5 structure and inhibits its structural recombination. On the other hand, the introduction of oxygen vacancy can speed up the charge transfer process, which is advantageous in the ZN migration and portfolio. We will discussing about the hybrid engineering of vertically confined marigold structure of RGO at vanadium diselenite as a cathode material for zinc ion battery. Here what we have done is, first we will be preparing the reduced graphene oxide and then adding the precursor for vanadium and selenide source, and later on the graphene oxide acted as a template and wrapped VAC2 on top of it vertically aligned together and form a novel structure of marigold like structure for marigold structure. Here in this SEM image you can able to clearly see that when compared to the AB, which is of pure vanadium diselenide, when addition of graphene oxide, it can be decorated uniformly as a marigold like structure. In the XRD and Raman spectra we can able to analyze that, we can able to see that the incorporation of reduced graphene oxide was present predominantly, and it was well known with the Raman spectra. D band and G band was periodically present in the hybrid material. Further X-phase analysis have been taken. The presence of vanadium in the mixed valence state is further confirmed with the existence of vanadium multi-vanadium peaks of V3 and V4 states. The SE3D spectrum specs at 56 and 55 equivalent to the SE3D pattern has been confirmed respectively, and C1s displays the three apparent peaks corresponding to 289 for C double bond C and C bond O and O bond C have been shows a variety of functional group found in the RGO, and for this we have taken a cyclic voltammetric curve for pure VAC2 and hybrid reduced graphene oxide and vanadium diselenide precursor at a fixed current rate of 1 millivoltage. You can able to see that at reduced graphene oxide and VAC2 hybrid, it shows an more predominant peaks have been present when compared to the pure material. So further we have been fixing the hybrid material with varying the current rate like 0.5125, and it shows an increased. This comparison of galvastatic charge discharge profile at various pure material and hybrid material shows that my hybrid material shows an extreme capacity when compared to the pure material, and with an stabilized rate capacitance performance and an 91 percentage of capacitance retenuation for a long cycle of 150 cycles at 0.5 ampere per gram. The key findings which I noted is that the reduced graphene oxide used as a template prototype is not only wrapped on the outer surface but also confined with a stronger penetration inside the VAC2 nanosheet. The outstanding rate performance and cycling capacity of the nanohybrid is due to the special marigold structure. The vertically confined marigold structure can inhibit the limited structural degradation. The RGO VAC2 nanohybrid decreased resistance and enhanced kinetics is due to the metallic conductivity of VAC2, which can be further produce zinc ions and effective electron transport path and further pathway. In summary and outlook, the in-depth mechanism of in situ characterization have to be studied well, like XRD, in situ XRD and Raman could be more useful for them. And in methodology, the unified activation mechanism like some metal ion doping and dissolution and intercalation of ions can be much more discussed. And varying of a key performance indicates with the activated material and initial weight, final weight, active center, and surface area all play a major role. The precision control of ECA parameters like current, voltage, time, cycle number also play a major aspect in it. Somehow, the newer strategies like surface modification, electrolyte optimization, structural design are being widely applied in the zinc anode electrolyte information in order to deeply investigate and interface and solve the problems regarding Z and anode. An in-depth understanding of interfacial chemistries, Z and deposition behavior, and their interrelationship are of significance for guiding the rational design of zinc anode electrolyte interface. Thus, the studies of stable interface and zinc dendrite suppression are promising direction to optimize several vanadium-based bimetallic transition metal dichalcogenate for aqueous zinc ion batteries.